All right, thank you, Sergi. So, hello everyone. I'm here to talk to you today about capsule systems. You may have been hearing this in the sort of buzz that's going around the deep learning community because it's kind of the passion project of Geoffrey Hinton for the last few years. Personally, I have been working with capsules for about the last month. The idea is we're hopeful that this sort of architecture can generalize well if we train machine learning models for image recognition from elevations that are kind of everyday, like very flat, and hopefully then these systems will perform better when the test data, that is what we're actually concerned about performance, is coming in from a drone, so at a different elevation. Unfortunately, I'm not at a point right now where I can share with you what exactly we've been doing, so instead I'm just going to be giving a quick introduction where I try to walk through all the intuition that I've gained from studying these for the past month. And this puts me in a little bit of a difficult situation because if I were sharing my own work, I could say that I was standing on the shoulder of giants. But since I'm not, I am instead standing in the shoes of giants, and that is actually rather more difficult. So I hope that you will be very casual with me and be willing to, challenge me, ask questions, and speak up at any time. And I hope that together we can come to a better understanding and maybe, grow with more excitement as to what we can apply systems or networks of capsules to. So to begin with, so what is a capsule? There's a lot of ways to think about capsules. A lot of people say a capsule is really a group or a column of units or neural units, but I really like to think of them as something really simple where for each unit you have really two parts of the activation. You have a sort of multidimensional, this could be a vector or a matrix, and this could be referred to as the pose, and you also have some sort of scalar. And if you think about a traditional neural network or a convolutional neural network, there's an interpretation of them that they act like feature extractors, where the features are kind of assumed to be hierarchical, right? And at every layer, the activations kind of represent the certainty that that unit has that the feature it's detecting is present in the image, right? And then as you go up to higher level features, depending on how the weights are, different combinations of these lower level features lead the higher level units to activate, giving their own score as to how certain they are that their feature that they're represented is present. And so capsules sort of generalize this because we not only want to capture the certainty that an object or an entity, as I'm going to call it, is present in what we're observing, but we also want to capture sort of instantiation parameters related to this. And so, for example, we could have just a vector of length 3 where the first element corresponds to the x spatial position, next one to the next spatial position, and finally one for the angle. In practice, this is not what happens at all, but it's a good way to sort of think about it to understand. Oh, it's working. Okay. Great. So I like to think about this sort of development from convolutional neural networks to then capsules and capsule systems as following a progression of sort of building in stronger assumptions into our very architectures. And the idea is that if these assumptions that we're making about the data, that is how it's distributed, what are its characteristics, if these assumptions are actually true, then we expect that our model should be able to generalize better, or it should be able to learn with less training examples, or something like this. So in a convolutional neural network, we assume that features that are irrelevant in one point in space are equally relevant when they're translated to another point in space. And this has proven successful for, let's say, classification, because a nose is a nose no matter if it's in the left corner or the right corner of an image. Capsules make even stronger assumptions. So we're actually assuming that really features or entities retain their sort of global identity throughout affine transformations, so that would be rotations in and out of the plane or viewed from different elevations, and really anything that the pose parameters can learn to represent in their vectorized form. There's also another aspect of capsules, and that is how they are routed. So eventually, the way that information flows from lower level capsules to higher level capsules becomes very sparse. And it's trying to build what is called a parse tree. That's just every it really means that every lower level entity that we're learning to represent has only one parent. And so my nose is only part of my face, and it's not part of like anything else, and building up from there. Okay, and lastly, there is a limitation in that it assumes that only one instance of a certain entity is present in the field of view that a certain capsule is acting on. And there's actually some motivation for the research for why this might actually present evidence for capsules is because humans experience a similar problem in our vision when we try to look at two identical objects that are very close together, and that's called crowding. Okay, so if you see a lot of really redundant looking sentences over here on the right side, that is because that's what they are. They're quite redundant, but I just feel like we need to get on the same page in terms of vocab. In particular, this is fairly new research, really just kind of two papers of relevance in 2017, one of them dynamic routing with capsules, and the other one would be matrix routing, matrix capsules with EM routing, which is actually still under review. So because of that, the vocab is a little bit all over the place. The terminology still hasn't been fully established, but I'll try to get us all on the same page going forward. So an instance would just be a single occurrence of an entity. So let's say like I'm looking over at this couch over here, and I have like a really narrow field of view, so I can only see these two people. So I would see like if I have a capsule that's detecting eyes, I would see 4 instances of eyes. So that's an instance. And then instantiation parameters would just then be, if you take the graphics point of view, it would be all those things on the right-hand side. What is used if you want to go from a graphics program to then draw out the thing, the parameters that actually change the output would then be the instantiation parameters. And this image actually comes from a very interesting research paper as well, which was where they tried to infer graphics program from images. So unrelated, but very interesting research if you're interested. So we already know that higher level entities are composed of lower level entities, and that it's going to be organized in this sort of parse tree. And really what I've been kind of skipping out on when I've been trying to intuitively describe what these pose parameters represent is that they're actually learned in training. So even though I'm saying, you know, this capsule is like looking at the eye, and, you know, the sort of pose parameters, the first dimension is the spatial coordinate, second is the angle. This is not actually the case. This is just sort of a mental tool. All of this stuff is learned discriminatively through using backpropagation to get the gradients, and then optimized with some sort of optimization algorithm. So what these entities and what the instantiation parameters learned are really well, you'll see later that they actually do come out in interpretable dimensions, but they do not necessarily have to. Okay, so I think one of the main reasons why capsules are supposed to be superior to just networks that output scalars at all points is that instead of learning features that are invariant under certain transformations, they actually want to learn features that are equivariant. So I'm going to be a little bit pedantic for the next minute and try to explain what equivariance is. So equivariance is just a generalization of invariance, and when we're talking about equivariance, we're really talking about a function or a mapping. But you really can think of it as a property can be equivariant, because in practice, a property is some function of the thing that it's a property of. Did that make sense? Yeah, okay. So equivariance is something that refers to a function, and we say that something is equivariant under some sort of transformation. And the condition for whether something is equivariant under some transformation is whether the function that we're interested in and the transformation are actually commutative. So if you look at this diagram to the right, to the left, on this side, we have something that's invariant. We have sort of two ovals and a curve, and you know we detect an eye, another eye, and a mouth, and this sort of blue arrow is some sort of labeling function or some property function that then classifies this as a smiley face. On the bottom, it's all rotated, but what you get is the same output. So we would say that this is invariant to the sort of rotation that was applied. However, on the other side, we could either rotate all the elements once and then apply the sort of labeling function, or we could apply the labeling function and then apply the transformation to it, and we would end up at the same result. However, a smiley face with a 30 parameter is not the same as a smiley face with a 0 parameter, therefore it's not invariant, but rather more generally, it is equivariant. Are there any questions at this point? Okay, but what I hope you take from this is that in order to sort of like capture this extra information, we have kind of like expanded the representational power of our features that, as you can see on this side over on the left, we not only sort of say what it is that we see, but we give some sort of parameter as to like the instantiation of what we see. So this is kind of motivating capsules. So, all right, and I guess going back to how this is an extension of CNNs, and in CNN we share weights kind of like this. You've probably seen a diagram very similar, and for I guess every filter that we want to build up in our next point of feature maps, it's really just the convolution, which if you flatten out the kernel and also flatten out the region that it's looking on, you just do the dot product between that. And when you slide it, you're still using the same weights that were used in the previous position. And so this is how some degree of invariance to translation is built into CNNs, as you've probably heard time and time and again. Okay, so far I've only talked about poses and these instantiation parameters very abstractly, and you may be wondering how is it that they're implemented? Well, I'm afraid to tell you that out of the 2 papers that have come out this year, they were implemented differently in each paper. So I'll just go through it one at a time. I mean, one obvious way to do it would be to use vectors, because vectors have direction, and that seems fairly interpretable. So you can see here, let's say we've got something that detects these sort of curves. So you can see the capsules over there on the left. They have their scalar, which indicates that they're highly certain that the entity they're concerned with actually exists. And then the vector that represents the pose, or the instantiation parameters, is rotated. And actually, sorry, the middle one should be pointing horizontally. Yes. Okay. Something else that's convenient about vectors is that they actually use just the really the length, the norm of the vector, to represent the scalar on the left-hand side. However, this was actually discovered to be a weakness by the next paper that built upon this. So instead, you can also represent the pose with a matrix, and one sort of motivation behind this is that it reduces the amount of parameters that you need in your mapping from your pose to the next layer's pose. Or as we'll discover, when routing comes in, you're actually mapping from a lower level pose to a higher level vote. And we'll understand what that means in a moment. So you can sort of imagine that if higher level entities are built up of a combination of lower level entities, then if all the lower level entities are sort of have like the same pose, that doesn't necessarily mean that the higher level entity is gonna, even be in the same dimensional space as them. So really we need to apply a transformation just the same way that we would, almost the same way, between layers in a scalar outputting neural network. And this transformation matrix, the idea is that after we optimize it, learning the gradients through a backprop, hopefully this will learn to represent the part to whole relationships between the lower level entities and the higher level entities. And so if we have poses of length 4, so 4 parameters representing our pose, you can see that if you were representing your poses using vectors, you would actually need quite a few in your transformation matrix just to get to the next layer. Whereas if you use matrices, if you organize them like that, then in general, as long as you're comparing square numbers to each other, you actually need only n parameters versus n squared in the case below, where n is the dimensions of your pose. Okay, so in matrix poses also, since we're not really using vectors, they don't really have this sort of vector length thing to use as a measure, the scalar measure of how certain the capsule is that an object exists. Now you could be thinking, why don't we just use sort of the L2 norm, or I guess Frobenius norm of the matrix? Really, their justification was that this was not good at distinguishing between, I guess, very close agreements and just close agreements. And we'll see what that really means in a second when I get to routing. So instead, the matrix capsules actually have a separate logistic unit. The first layer, it just takes scalar weights from, I guess in the primary capsule layer, it takes scalar weights of the first layer, the same way a regular neural network would work. And the next layers after that, the scalar activation part is actually learned through the routing algorithm. Okay, so what is our whole motivation of getting to this pose space? The idea is once we get into this sort of space where these poses exist, then everything is kind of linear from there on. If you remember my sort of contrived example from the first slide where, you know, we just had 3 elements in this sort of list and they were directly corresponding to sort of meaningful parameters to us like x, y, and elevation, then you can imagine that if you wanted to change these things, all you would have to do would be to, you know, either multiply it by some sort of matrix or, you know, add another vector to it. And so these are all sort of linear operations, and this is a good thing, hopefully. However, if you think about what sort of changes that would happen, that would cause in the actual input, which is really, if you're looking at images, a bunch of pixel intensities in a, you know, a 2 or a 3D array, then this is actually, these sort of simple operations such as even rotation would be highly nonlinear. We would hope that yes, they do all lie on some sort of manifold, but we really can't expect it to be linear. That is the justification behind really the layer before the primary capsule layer in both papers so far, which is, has a ReLU activation. However, you should really keep in mind that all the capsule layers do not have nonlinear activations. They're just completely linear. And the idea is if we've really learned to go into the space of poses, then we've done inverse graphics from there, is what it's called. And now everything moving onward should be linear. Okay, a small word about place and rate coding. In particular when it comes to where an object is in space. So again, referring back to the first slide, you could directly have this as an element of the pose. However, this is not how it's done in practice. In practice, you would have a sort of a grid of capsules of a single type, and then you would expand that grid out however many types of capsules. And by type, I mean you would hope that all capsules of one type would fixate on the same sort of entity. And so that leaves you with how do you actually encode information for where something is in space. And so there's 2 ways to do this. Place coding, would actually be when if an object or a feature moves in space, then actually a different capsule in the grid activates. And so this would be encoding this position using place. Whereas with rate coding, if this movement happens, then the same capsule will activate, but the orientation of its pose will be different. And I hope that's somewhat apparent. Out of curiosity, did anyone attend my talk last week at the Applied R meetup? Okay. You may remember there I said that I'm terrible at drawing ovals and rectangles, and so therefore I used everyone else's diagrams. Well, I've decided to start trying to overcome that, and that is probably why these are very hard to comprehend, because I drew them myself. Interestingly, while we're on this tangent, I've become aware that this is actually a skill that a lot of people have and learned in their education, but I was a physics major, so instead I learned Greek. So I hope you'll bear with me with my, my poorly drawn geometric shapes. Okay, so in capsules, how this fits in once again, in the lower levels, spatial information, spatial location is place coded, while in higher levels it then becomes rate coded. Okay, and just a small point, in the 2 implementations of capsules that have been done by researchers so far, they actually want to encourage the first 2 dimensions of the capsule poses to have spatial information, and this is higher on in the higher level capsules, and they do this by explicitly adding the spatial coordinates to the first 2 dimensions when you reach the last capsule. And so this is sort of a way of trying to nudge that last capsule in the position of rate coding this spatial information. Because as I said earlier, we don't have too much control over what the dimensions of the pose will learn to represent. So this is one way of trying to exert some control over that. Okay, so now here's, I guess, the second innovation that capsules really bring about, and that is trying to really learn a more sparse representation or learn a more sparse network structure and represent sort of high-level objects through this parse tree that we've been talking about. And this is done in actually, I think, a very beautiful and elegant way, and that is when the lower level capsule tries to decide where it sends its information in the next layer, it will actually eventually iteratively learn to send it to a higher level capsule that it expects will have a high activation if it sends this information. So for example, if a lower level capsule actually learns eyes, then it would over time be more likely to send it to a higher level capsule that is representing faces, because we would expect that if other lower level capsules send the right sort of features and their sort of part to whole relationships all match up, that is, they're all aligned, you don't have like your nose above your eyes, then this higher level capsule will also have, it will also activate. So this is how it's done. So again, there's going to be a little bit of vocab here, and unfortunately it's not the most transparent sort of vocab. So let's assume we start from the poses of the lower level capsules. After you apply the sort of part to whole relationship through this weight transform, weight matrix, then you would get the vote. And so every type, I guess every lower level capsule sends a vote to every capsule in the layer above. And of course, this no longer becomes the case if you want to share weights as convolutional neural networks do. But for the moment, let's just assume that every capsule in layer L sends one vote to every capsule in layer L plus 1. And this is every capsule both on the grid of where all the capsules are the same type, and also by depth, where every capsule is a different type, looking at a different sort of object. After we get these votes, there's actually a routing coefficient, which shows how strongly this information is then sent to the higher level capsule. So even though the vote is what we call the thing that comes out of the weight matrix multiply, the routing coefficient is what seems to me to subjectively seem more like a vote. Any questions at this point? Okay. Yeah, so once again, just to review how the capsules are going to be organized in the array. So here I'm using matrix capsules. So here we have a 2 by 2 matrix representing the pose of one capsule. And then for that one capsule type, it is gridded through space. So we have, for this first capsule type, we have 4 of these capsules in this layer. And then there's also a depth. So where you've got this grid of a capsule type and then different capsule types kind of going down in each layer. Okay, and once again with some vocab, the vote has also been called a prediction or a prediction vector or a bet, because capsule researchers like to personify their capsules a lot. That's why you hear a lot of language of the capsule prefers to send its information to higher level capsules that will agree with it or have a higher activation when combined with what other lower level capsules were sending it. Okay, and to try to bring this routing concept down to earth, we've actually experienced routing in CNNs already, is where the routing is really, if I had to describe it, it's routing by who is the loudest voice. So when we implement a max pooling layer, we're really discarding all the quiet voices, the scalar values that are lower than all the rest in the region, and we're just letting the loudest one route to the next layer. So this is really just kind of a primitive form of routing, so it's not completely new. Okay, so no need to get intimidated by this thing. It's actually a fairly understandable algorithm. So this was how the most recent research paper on capsules and the one that my colleague and I have been trying to replicate for our work with drones. This is how it implements the routing. And this is actually a clustering algorithm. The way it works, I guess sort of how it's organized on a very high level, seems very close to the k-means clustering in that it alternates between two different steps. And we'll see exactly what those two steps are kind of in the next slide. Okay, so all these triangles here would be votes coming to a higher level capsule. And what this would represent would just be 2 dimensions of the votes coming in. And so in an E step, we really assume that they should be distributed in some sort of Gaussian. And that means that when we consider all capsule types at once, then all the votes are really distributed in a mixture of Gaussians. But we'll really just stick to looking at it in a single capsule. So in the E step, we really try to estimate the mean and the variance of this Gaussian. And then in the M step, we update our parameters to try to better fit what we had calculated in our E step. And so you can see that things that were farther away from what we predicted the mean and variance of the Gaussian to be, then the parameters associated with them are adjusted in a certain way. And to bring this down to earth with capsules, the parameter that we're interested in would be the routing coefficients, and by adjusting them if they're far away would just mean decreasing their value, which means that capsules that apply this vote to a higher level capsule will be less likely to send as much of a vote to that same capsule in a future iteration. And this kind of goes on. In practice, 3 iterations of each step are implemented between every layer in the matrix capsule paper. Okay, so yes. Okay, yeah. So that's because a large part of their parameters that we're learning discriminatively is that weight matrix that is between the poses of the lower level capsules to the votes, and these are the votes. And the idea is that if we really want to minimize this and we associate really a cost with being far from the prediction, then that weight matrix really learns to transform everything from the lower level capsules so that when they're in the higher level, the votes are now in the same sort of coordinate frame. And so that's why if these lower level features indeed do belong to the same feature, we would then expect them to be very close in space. But if they don't, then we would expect them to be very far. And so this is actually a form of, this is actually what I find the most elegant about the routing, because this is performing coincidence filtering. The idea is that a lot of multiple high dimensional lower level features we don't expect to coincide when we send them to like another high dimensional space, just because the curse of dimensionality and all that. But if they're actually part of the same thing and their poses are aligned with each other such that after they each go through their transform, they are close in space like this, then we do actually have some reason to believe with confidence that this higher level feature does indeed exist. Right? Whereas to do it more naively, such as in convolutional neural networks, we really just have evidence that's very independent, right? So we see one feature is present, we see another feature is present, and we see another feature is definitely not present. And just based on these sort of values, where we don't know anything beyond this sort of score, we say, okay, now this higher level feature would be present. And so we can feed in some like very unrealistic looking things where the eyes are like way too far away from the nose. Whereas this really, because of how high dimensional the space is, we expect lower level features to agree in their poses, I guess in their votes, which is the pose following the transform. Okay, so I guess this is always a good thing when considering a new architecture to really get down to earth about what are the inductive biases associated with. And of course, there's also stuff like smoothness assumptions. But in particular, when it comes to routing, we're using the principle of the minimum description length, which you can also think of as a more well-principled form of Occam's razor. And that is that in the EM algorithm, what I kind of didn't mention is that if we just implemented a vanilla EM, we would assign every single vote to like one Gaussian in the mixture. But really, it might be the case that some lower level features are just completely irrelevant, and we want to be able to discard them. So what's actually going on, what the mixture is actually, it's a mixture of a number of Gaussians, which that number is equal to the amount of higher level capsules, and then under all that is a sort of like uniform distribution, such that if a vote from a capsule was actually irrelevant in the context of being part of a higher level feature, then we could just explain it as being part of this uniform in the background. And the idea is we impose sort of a cost. There's a cost for explaining something of being part of this uniform, and there's a cost for explaining a vote for being part of a higher level capsule, right? And so you can imagine that if a vote is very close to what we've estimated the mean of what a higher level capsule's votes should be, then that should be like a relatively low cost. If it's kind of like farther away, then that should be a higher cost, and being part of the uniform is sort of like a background, sort of low cost. And so this sort of assumption is just us following the minimum description length, imposing a model that selects for this sort of behavior. And also, when we implement the loss at the final layer, there is a second sort of inductive bias. And if you're unfamiliar with inductive biases, just to very briefly recap, if you think of selecting a machine learning model, with parameters or even like parameter free, it's very unfeasible to search through really the space of all possible hypotheses if you think of a model as a hypothesis. And so the inductive bias is really just in this space of hypotheses to what sort of models and what characteristics will you gravitate towards. And so in this case, we prefer things that either explain a lower level vote as part of a tight cluster or just being irrelevant, and so that's minimum description length. And also, when it comes to our output layer capsules, we really want the outputs of the capsules representing the correct class to be very, very far, or as far as possible, from the outputs of all the capsules that represent an incorrect class. So in case it wasn't clear, in your output layer, you will have the number of capsules that you have would just be equal to, if you're doing a classification problem, the number of classes that you're trying to choose between. And because of this sort of intuition, and this also ties into the routing, what sort of behavior we want to learn in the routing through training. So we just impose this second inductive bias, and this is just done in the choice of the objective function, which is kind of like a version of margin loss, or hinge loss you might be familiar from support vector machines. Yeah. Okay, so just very briefly, I want to talk a little bit about the experimental findings, and these are the things that I was working with my colleague to reproduce before applying it to our drone data. So capsules have been shown to be like highly effective at segmenting highly overlapping digits. And so this, I'll show in the next slide, while this is actually expected behavior for capsules. And this is because of the fact that they build a parse tree and try to make sure that everything is then belonging to this tree. And in the matrix capsules paper, that was done on the small NORB data set, which is just 5 toys, a number of pictures of 5 toys taken at many different angles. And I think the most impressive result, which was the motivation behind me getting into capsules, was that they were able to train the system on a set that was where the training set only included a limited range of all the azimuths and elevations included in the data set. And then the test set included the angles that it was not trained on, and it actually generalized very well. And I almost want to call this sort of true extrapolation, although I won't go that far. Also, the pose dimensions have turned out to be kind of interpretable. In the dynamic routing capsules paper, they attached sort of a decoder network to try to decode the outputs of the intermediate capsule layers, and then they would fix all the capsules and sort of, perturb their pose parameters by a little bit while keeping all the rest of the parameters fixed. And it showed some sort of like natural variance across dimensions that we might expect, such as the thickness of a stroke or the loopiness of a certain line, things like this. So it does show some interpretability, but I again want to stress that when this gets scaled up, hopefully it does get scaled up to more complicated images. This is not something that we should take as a necessity because of the fact that the pose parameters are learned. Okay. All right, and here is again one of me trying to work with basic shapes for your entertainment. So why is it that capsule systems are good at highly overlapping? And that's because they're capable of doing what is called explaining away. So we see here, we've kind of got 4 ovals, 4 ellipses, and 2 curves. So in the middle here, is that like an upside down smiley face? And let's assume that we have 2 classes, smileys and sad frowny faces. Yeah, I mean, that's one interpretation, but now our curve on the bottom and our ellipses on the top are left without parents. So we would expect that if we're learning some parameters related to routing and also others just learning iteratively through the inner loop, that this sort of behavior would not, this is not a prediction that we would expect a capsule system to make. Well, on the other side, we can see the correct interpretation of this would be to have, a frowny face on top and a smiley face on the bottom. And so doing this act is called explaining away. In the literature, I'm actually not sure why it's called that. I'm sure it's for some historic reason. And if anyone knows, please speak up. And again, with these parse trees, we assume that every entity only has one parent. So images like this would not be acceptable, where some of these lips are part of like multiple things. Okay, and before I finish, I just want to address what might be the growing elephant in the room once I showed you the experimental findings, and is that should researchers still use MNIST? In the machine learning community, there's sort of the idea that over time, the benchmark data sets that we use become sort of stale in the same way that people can overfit to their development sets. You can also eventually fit to the withheld test set of a benchmark. And so there's the idea that new benchmark data sets should be created with enough frequency to ensure that old ones don't become stale. However, I think this is not really the full picture. I think there's still a lot of value in these old or small data sets such as MNIST and SmallNorb. And that's because I guess these results, although it was shown that capsules were able to compete with the state-of-the-art results on MNIST classification, that's not really what the results are showing. The researchers went into the work with some assumptions, which they built into the architecture of their network, and they expected their network to display certain properties based on these assumptions. And these would be things like building parse trees to then explain away what highly overlapping entities belong to, what they are. And so that was shown in one paper. They also thought, okay, well, if we really do find this pose space, then it should be very robust to affine transformations. And so that is what the researchers that worked with the SmallNorb dataset also represented. So I think there is a lot of room for still using data sets such as MNIST for these sort of laboratory purposes. And I would really encourage people to not speak too dismissively of them, because there is a little bit of a danger where everyone becomes obsessed with beating the current state of the art, and so they do maybe very hacky, unprincipled type adjustments. They perform better, then try to after the fact explain it. So there's a danger of running into that sort of research. And I would just encourage everyone to take some time once in a while to think about how data sets whose really characteristics we understand well can be really leveraged to develop new systems that out of the box might not perform better than the state of the art, but maybe in a few years once engineers get interested will be competitive. And so if you want to start with capsules, I have a few, I guess, resources here. So the first GitHub link is a person from China, actually I think he's a biomedical engineering student, but he is working on a library for capsules. Now it's still, this is still a project that's ongoing. So again, I really encourage anyone who's interested to try to get involved, read through the research, and see if maybe, open a pull request to this guy. I'm sure he would appreciate it. Also the second one, this is a very good starting resource that I'd recommend. It's a Jupyter notebook. actually by Aurélien Geron, which he wrote, I think, forgot his book. It's an O'Reilly book with introduction to machine learning with TensorFlow and scikit-learn. So very good source there. I think there's also a couple YouTube videos that accompany the notebook. And finally, Shifeng Guo, in his Keras implementation, the README is a really good source of other resources because he kind of lists out all the other implementations. And if you also want to get started, well, I hope that you also won't hesitate to maybe email me or get in contact, because even though I wasn't at a point today where I can share what I've been doing, I have really been spending a lot of time with these capsule systems in the last month, and I'd love to get other people up to speed. I consider it a little bit of a passion of mine to try to bring what's used in production and what researchers do closer together. Same with the GANs, trying to make what might be thought of scientist curiosities more applicable. So please don't hesitate to get in contact with me. And that is all I have to say. So thank you very much. Any questions?
Anybody can ask some questions? Yes, Martin.
Hi, thank you for the time you took to explain this. It's really appreciated. There is something that I do not really get completely to the bottom. Can you go back to where you defined equivariance?
You mean the
yeah, it's easier if you just go to the slide, because then we can understand a bit better. But essentially you said that, no, way before. It was at the beginning. Yeah, still a bit.
Did I pass?
It was way before.
Okay.
Sorry. I had to think about it. Yeah, this here.
Okay, yes.
So, sorry, it was at the beginning. So you said that the function that you, so you were saying that you want to have a representation that is equivariant to these operations,
Yeah.
which I assume are rigid translation and rotation, or is it something different?
Yeah, we really assume it's the sort of operations that you could do with a graphics program.
Okay.
Yeah.
But rotation around a fixed point and translation are not commutative. So, meaning that, for instance, if you take that smiley face and you just rotate around each piece center, so let's say that the two eyes just rotate 90 degrees around their center, and the mouth rotates just 90 degrees.
Yeah.
It's just a mind experiment. I'm thinking, would that result in the same activation of your capsule network?
Right. Yeah, so when we're talking about equivariance, we're talking about one function. So in this case, the function that outputs the property we're interested in, and one transformation. So it's just the function and the transformation that are commutative with each other. It doesn't mean that the transformations have to be commutative if they're done in sequence. Sorry, could you repeat the second part of your question?
I'm just thinking, if you have to find a face there, you need not only to know if the eyes are aligned in a angle wise with each other, and there is a mouth in that angle, but also know that the relative displacement of the two eyes and the mouth needs to be the same to make a face that is consistent.
Right.
But if translation and rotation are not commutative, then it means that you could have one eye here, one eye there, and the mouth somewhere else, still aligned by the angle, and still aligned translationally, but not having a face.
Right. Yeah, so I can't really speak to like how linear we expect this to be, but when it comes to, let's say, a translation and a rotation, what would really happen would be since we place code translation in lower levels, then we would really just be learning the same. Let's assume we have a higher level capsule, then we would be learning the same transform between this, let's say, that pose, and let's say the pose over there, going the weights that correspond to these poses, going to the votes to the face higher level capsule, then those weights would just learn to be the same.
Yeah, I mean, it might be a bit too deep for for a question, but yeah. Okay.
Hi. Yeah, thank you for explaining all this. I have also the question related to equivariance. It's very exciting that, you know, especially in the sense that we are making our deep learning algorithms less stupid, if I am bold to say that.
Yeah.
What I'm curious is, since, you know, before we just wanted our algorithms to just, you know, remember that, you know, these things are same. Now we wanted to also sort of learn these angles and this translation. Wouldn't it require higher amount of training data just because it's learning more about the objects?
Well, because we're actually building this sort of assumption that what we're concerned with is the same after these operations, we're building that really into the architecture itself, whereas the current way of teaching a model that is to augment or build upon your data set with, you know, adding to your distribution with the data that's gone through the transformation that you want to teach your model is the same afterwards. So really, this is the reason why we can train with less data.
Okay, and was this proven in the last experiments, or this is the intuition that we would need less data?
Yeah, so far the experiments on the MNIST and small NORB dataset have shown to be more data efficient, although their peak accuracies are not yet, you know, the best. It is a result that so far looks promising. However, I would of course encourage you to be skeptical, as you should.
Yeah, but definitely. It's a neural network, so I guess, you know, it would take time to get to the best part of it.
Yeah, I mean, in particular to me, like, this sort of method of explaining what we want capsules to do with saying what really this whole parse tree and part-to-whole relationships that we're learning is something that this representation is capable of learning. But to me, so far in that I've looking into it, there's no reason for me to suggest that this is what it's going to learn necessarily. Beyond that, we hope that this is an optimal configuration and that using gradient descent we can find it. But it might not be the case, especially with more complicated data.
So thank you very much. It was a really great talk. I have a little bit of a silly question. I think this might be interesting for you, because every time I see new neural network architecture, I don't know if it's just me, my first question is, can I build a GAN out of this? So my question, I guess, would be, seeing as this is kind of an expansion of CNN and also like use like inverse graphics going on here, I'm already feeling all my GAN senses tingling. Are you aware of any like work in that direction, or do you think that would be a relatively straightforward thing to experiment with?
Okay, well, it would be definitely straightforward to make the discriminator. The generator, I'm sorry, I'm not really sure right now, but that's a very interesting idea. And yeah, now I'm curious as well. Thank you.
Thanks for the talk. Just a quick question. You showed capsule nets used on image recognition. Is there any use case on text comprehension tasks? Because, you know, you can also use CNNs on text and kind of works. And you also mentioned it has a similar mechanism to attention. Yeah. So, yeah, is there any use case for that?
Okay, yeah, so I think the assumptions that were encoded into the architecture were made with the sort of visual domain in mind. However, you know, the whole word parse tree, I think, actually it's used a lot in linguistics when, you know, every word is a part of speech and all. So I think it's definitely possible. But as I said, right now there's just 2 papers, and one of them still under review. And so again, like I encourage you to maybe test this out for yourself. Or if you have an interesting project, bring it to me. I'd be really happy to sort of experiment.
Cool. I think it's the last one. You were stealing my word. The last question.
Okay, another thing that I was curious about is that the use of max pooling is probably, the worst part about CNNs. I could be wrong. I'm not that deep into it. But could it be that the routing algorithm that is proposed here, it can be used together with the CNNs that are already there instead of making a capsule architecture? Would that work as well?
It definitely not with significant amount of adaptations, just because outputs from CNN units are scalars, so they don't really have a position in a vector space beyond just like dimension 1. So.
Okay. Yeah.
Yeah.
Thank you.
Cool. Round of applause for Raymond. Thank you. So we're gonna have, 10 minutes break. If you feel bored, or if you feel that you have some questions about Stylight, we have some people from Stylight. There is Marco, Stefan, and also Noemi, who is spending his evening with us as well. So if you have any questions, just approach anybody of us. Yes, and we have 10 minutes break, and after we continue.